Welcome to Expert Tutorial. My name is Dr. Flash, and in today's video we are going to be learning something new, simple harmonic motion. Okay, majority of you might be finding it difficult to understand this topic, but I assure you, after this topic, you should be able to answer questions on it. Okay, now simple harmonic motion is the motion of a body in which its acceleration is directly proportional to its displacement. Okay, which means that an increase in displacement causes a corresponding increase in acceleration, or an increase in acceleration will obviously cause an increase in displacement. Okay, now we're actually going to see how this is actually true, meaning that we are going to be proving some formulas and also taking some things that are associated with simple harmonic motion. Examples of bodies that undergo simple harmonic motion include the motion of a bouncy ball, the motion of a simple pendulum, a helical spring, and so on and so forth. Now let's take some useful terms in simple harmonic motion. The first one we're going to take is frequency. Frequency. Now frequency is the number of oscillations performed in a given second. Okay, mathematically frequency is written as F is equal to N over T. Okay, number of oscillations performed in a given second measured in hertz or in cycles per second. Okay, these are basically the two units for measuring frequency. Now you should know that N means cycles. Okay, the number of cycles produced or the number of revolutions formed in the motion of the body. Frequency mathematically is also given as N over T. The next one we're going to talk about is period. Period. Now, in our normal world, we already know that period means time spent, but in simple harmonic motion or in physics, we define period as the time taken to perform one complete oscillation and also measured in seconds. Okay, time taken to perform one complete oscillation. So basically, we don't actually need to count the definition. Looking at the formula T over N, time taken to perform one complete oscillation for frequency, number of oscillations over time, or number of oscillations performed in a given second. Looking at these two formulas, you can see a relationship. Period is T over N, small letter T over N, and frequency is number of oscillations over T. That is N over. So you can see that they are both reciprocals of each other. Okay, period is big letter T. So from here we can get a relationship. Mathematically, we can say that period is equal to 1 over frequency, because obviously if we switch this guy, we have to switch the next side. And T over N gives you period. So 1 over F is equal to frequency, or frequency is equal to 1 over period. Okay, this is the relationship between period and frequency. There are other terms that I would like us to talk about, but first of all, let's talk about the motion of a simple pendulum. Let's say we are having a simple pendulum, and the simple pendulum is at rest. Okay, if this bulb is at rest, that it is not moving, meaning that its displacement x equals 0. If its displacement x equals 0, it means that this bulb is at rest. So what I want to do is apply a force to this particular bulb. That is, I'm going to be displacing it either towards the left or towards the right. It doesn't matter which part we are displacing it, provided that a force is applied to the bulb and it is causing the bulb to move from its position. Now you notice that if this bulb moves to this end, we are going to be having something like this. Okay, initially the bulb is there, and then I displace it down to this part. We are going to be having a system like this at a very small angle. Let's displace it with a very small angle itself. If I should release the bulb is not going to remain there. It is going to fall back, not resting at this point again, but passing through this point rather. It will pass through this point and come to a point on the other side. Okay, the same bulb comes to a point on the other side. Once it gets to this point, it tends to fall back, passing through the origin again, going back to the extreme end. Therefore, as it is moving to and fro, we see it is undergoing a simple harmonic motion, because obviously the simple harmonic motion is also called a to and fro motion, okay, or oscillatory motion. So as it is moving to and fro, we consider it a body undergoing simple harmonic motion. There are some parameters or terms on this diagram that we should take note of. One of them is, you should take note that as the body moves from this point down to this extreme, when it comes back to this point and then back again, it will not get to this exact point in which I left it after displacement, but rather it is going to come to a point just before it. Okay, this is because frictional force in the air is dissipating the energy. Okay, there are forces in the air which causes the simple pendulum to lose energy, causing it to fall back to rest. So at a point it swings to and fro, causing the bulb to return back to this initial position. But you have to know that at this point there are certain quantities that vary also at this point. Now watch. At this point we have the maximum velocity of the body. Why is the velocity maximum? Let's take an instance. If I should release the bulb at this point, it swings passing through this point. Now we notice that anytime it passes through this point where the displacement is 0, it passes there with a very high speed. Once I lift the bulb, it starts increasing its velocity, Once it gets to this point, it passes there with a very high speed. Therefore, we can say the velocity is maximum at this point. Okay? And at this point, velocity is minimum because when the bulb swings to this point, it tends to stop for a few milliseconds. Okay, it comes to rest. Its velocity is minimum or the velocity is equal to 0. Now what about amplitude? We already know that amplitude, which is number 3, amplitude is the maximum displacement from equilibrium or mean position. You don't still have to count this definition. What does it mean? Maximum displacement means the highest displacement. Mean position or equilibrium means where the bulb is at rest. This is the mean position, the center between these two guys, mean. And where it's also at rest is what we call the equilibrium position. Okay, now as the bulb moves from this center to the extreme, we are going to obtain the maximum displacement. Why is this point called the maximum displacement? Don't cram it. Look up. As the bulb moves from here to here, it covers a distance x. The reason it is called maximum is because this point to this point is the farthest distance it will travel. That first distance it travels is the maximum displacement. Because if the bulb moves back, comes here again, it is going to stop here before returning back to this position again. So it will not get to this extreme because energy has been lost. It will get to this point and then it swings back, go again, swing back until it comes to this point where it starts remaining at rest. Okay, and no force is being applied anymore. So at this point we have what we call the maximum displacement. Okay, we can say displacement is maximum at this point and displacement is equal to the what? The amplitude. Amplitude is maximum displacement. Anytime displacement is maximum, we obtain the amplitude of the body undergoing simple harmonic motion. Now, we just have to take note that whenever a quantity is maximum here, it has to be minimum at the other point or 0 at the other point. And whenever it is maximum there, it has to be minimum at the center. Okay, same displacement is minimum here or equal to 0, and on this point is maximum and it equals amplitude. And here velocity is maximum, velocity is minimum at this point. Okay, we also have to take note that acceleration is maximum at this point. So obviously it becomes the opposite here, because if it is maximum here, it is minimum here, and if it is minimum here, it is maximum on that point. So acceleration at this center is minimum. Okay, also another thing we have to take note of, the body gaze height at this point. This one is particularly useful when we want to calculate potential energy. The body gaze height at this point, but potential energy is equal to mgh. Okay, now we've talked about a few parameters with the simple harmonic motion. We have frequency, we have period, we have amplitude. Another thing we're also going to talk about is the velocity. The velocity of a body undergoing simple harmonic motion. Now, this motion that is being undergone by this pendulum in this case, it is not a linear motion. Okay, because the body is not just moving in the x and y axis at this point only. It is undergoing what we call a curvilinear motion, because if you take a look at the direction traced out by this part, it is a curved path. This is a curved path. Okay, don't mind the diagram, it's not drawn to scale. So what we are seeing is a curved path. Okay, or we can say it is half a circle, because the circle is also a curve. To get the velocity, since it is a curvilinear motion, we are not going to take record of the displacement in calculating the velocity. And since the angle is very small, we will see that this plate is exactly a curve. The angle of displacement must be very small. Okay, now the velocity is defined as the ratio of the circumference traveled by the body to its period, because period is the time taken to complete one oscillation. So we have to divide the circumference of the circle, which is distance, measure the meter generally, by its period to get the velocity. Okay, Seeing this half circle, to complete it, the body has to travel twice. It moves and forms a half circle first, then forms another circle when it goes to and fro. Now, when I combine these two, I'm going to get an approximately full circle. Okay, so the ratio of the distance covered by this circle to its period is what we call the velocity of the body. So velocity mathematically is giving us 2 pi r divided by period, where r could be x, which is the distance of the maximum displacement to the center, or we can say it is the amplitude. Okay, 2 pi r over period gives the velocity of the body undergoing simple harmonic motion. Also, there are other parameters that are very useful that I would like to talk about in this course of study today. The next thing we'll be talking about are the equations of a simple harmonic motion. Okay, equations of simple harmonic motion. These are some very useful equations, and whether you are going for an A-level or an O-level exam, these equations will be particularly very useful for you. And also, you have to take note of the parameters that I've talked about in the diagram. Now, looking at the body, the first equation we're going to take is displacement as a function of time. Displacement as a function of time for a simple harmonic motion is given as A sine omega t plus phi. Of course, you should know what phi is. Phi is the phase angle, omega is the angular frequency or angular velocity, and t is time. Now we are seeing that this equation has to do with sine. It's a function of sine, and it's very easy for you to remember. You don't need to start confusing it with the cosine function. Okay, simple harmonic motion S, and the wave equation starts with S, telling you that it is what? Simple harmonic. To get the velocity of this body undergoing simple harmonic motion, we have to take the derivative of the displacement with respect to the time. Okay, derivative of displacement with respect to time. So taking the derivative of the whole equation here with respect to time, dx over dt gives the change in displacement, and it is equal to, now to differentiate this guy, we have what we call the function of a function. If you don't know how to differentiate, I will advise you guys to watch the previous videos on explicit media on how to differentiate functions. Okay, everything has been taught and they are there. Now let's differentiate what they are saying here. First of all, we differentiate what is in the bracket. Phi is a constant phase angle, okay, measured in degrees. So I'm going to differentiate the constant, gives me 0, which is unimportant, and differentiating omega t, the t vanishes and I'm left with omega, and then omega multiplies whatever is outside, as far as what is outside does not contain what we are differentiating with respect to. So assuming what is outside is having a t, we will have made use of product to differentiate. Okay, so now we differentiate what is inside. Wt being differentiated gives you w, or omega rather. So it multiplies what is outside. We are going to obtain aw. Now when we differentiate sine, you get cosine. Okay, there is also a proof which is on our mathematics video. We get cosine, and the function remains the same, omega t plus phi. Although in some examinations they don't make use of the sine function, they make use of the cosine function. That is, they tell you that displacement is equal to a cosine of wt without a phi. Okay, that's the difference between these two equations. So anyone you see, you should know that this is also correct. The x over dt is equal to a omega cosine wt plus phi. Now the x over dt, you should take note that the x over dt is the velocity of a body. Okay, so we can mathematically say that velocity equals this equation. Now this equation is used for calculating the velocity of a body undergoing simple harmonic motion at a point in time t in space. Okay, at a point in time t in space, when we know the time, we know the angular velocity and every other variables we are seeing here, we can get the velocity. Now, how about the acceleration? Acceleration is the derivative. Acceleration is the derivative of velocity, first derivative of velocity, or it is the second derivative of displacement. Okay, you should take note that acceleration is first derivative of velocity or the second derivative of displacement with respect to time. So if I'm to differentiate this equation on the board, I'm going to get the acceleration of the body undergoing simple harmonic motion. Therefore, acceleration equals dv over dt or d2x over dt squared, which is the second derivative, and it equals differentiating this equation again, or this expression rather. Okay, we are going to differentiate it the same way we differentiated the first one. So differentiating omega t, you get omega, multiply what is outside, we are going to get minus a omega squared. The reason for the negative sign is because when you differentiate cosine, you get sine. Okay, you get minus sign actually. Okay, when you differentiate cosine, you get minus sign. That is why the minus is outside. So sine, and we write what is inside, we get omega t plus 5. Now looking at this equation I just obtained again, you will notice that the equation actually looks familiar. What does it look like? It looks like the first equation we had before. We can see we have a sine wt plus 5, which is the same thing we have here. Now a sine wt plus 5 is what we termed displacement initially. Okay, so I'm going to be substituting or writing this equation first as minus omega squared a sine omega t plus 5. Okay, a sine omega t plus 5. Now a sine omega t plus 5 is what we term displacement. So if you recall, this quantity here is what we refer to as displacement. So substituting back into that expression in the board, acceleration will equal minus omega squared x. This is the formula for calculating acceleration. Now initially we define simple harmonic motion as the motion of a body in which the acceleration is directly proportional to a displacement. So we cannot see it here that acceleration is directly proportional to displacement x. It is very obvious. That is why we don't have to count the definition. Okay, now the acceleration at this point could be anywhere, okay, where we know the value of the displacement because the angular velocity tends to remain the same. Looking at this diagram, we know that the acceleration is maximum at the extreme, like we said. Acceleration is maximum at the extreme and minimum at the center. Maximum acceleration is obtained at the point where displacement is maximum. You notice that where we have the maximum acceleration, displacement is maximum at that extreme, and when displacement is maximum, we get the amplitude. So to get maximum acceleration, all we are going to do is replace the normal displacement with the maximum displacement, and maximum displacement equals what we termed amplitude. Therefore, maximum acceleration is minus omega squared a. This is the formula for calculating maximum acceleration. Okay, now looking at this formula, you don't have to bother about the negative sign. The negative sign is simply telling you that when we displace the body to an extreme end, okay, the displacement is in this direction, for example, the acceleration is going to be directed back. That is the opposite to the displacement. That is what the negative sign is telling us, that the displacement is directly opposite to the acceleration, okay, or acceleration is directly opposite to the displacement. Now this will be the first part of the video we are going to talk about. On our next video, we are going to talk about the other equations on simple harmonic motion. Next video, we are going to be talking about the mechanical energy, the kinetic energy, and how they all vary on a simple harmonic motion. Okay, please make sure you like this video, subscribe, and also share to your friends. Do not learn alone. Share to your friends and let them learn also. If you are a UTME student, if you are an A-level or an O-level student, do well to watch this video as it will help you for your physics 113 or your simple harmonic motion examinations in general. Thank you.